So at this point, we just learned Fourier series. Yeah. Fourier series expansion. All right, so last time we learned more properties. Yeah. All right, so now we move to Fourier integrals for even and odd functions. Yeah. Last time we learned Fourier series extension for even odd functions. Yeah, even odd. So here you can see the even odd function. These two type of special simple functions play a very important role here. Yeah. So we continue. So this time we get to the Fourier integrals. Yeah. Let me recall a little bit the last a few slides about Fourier integral. Yeah. Why we want to study Fourier integrals? Yeah. Because after we learn the Fourier series, we know it's very important tool to represent periodic function. Yeah. Yeah. Look at the targeting functions, periodic functions. So the question is, in the real world applications, although many functions can be represented in periodic functions, but also many functions cannot be represented in periodic functions. So we also, our problem-solving tools, we also need to cover those non-periodic functions. So for that reason, we want to extend Fourier series expansions. We use integral to calculate Fourier series coefficients. But those integrals, each integral, the definition of each integral is on one period of function. One period, from negative pi to pi, and the general case from negative L to L. That's the limitation. That's the limitation we want to remove. So for that reason, we introduce Fourier integral. Fourier integral, so we do not require periodic function, and the interval we stretch to the whole x-axis, from negative infinity to positive infinity. Then we can cover more functions, more general functions. Yeah, so that's the story from previous a few slides before we get this slide. All right. Then, Julia, yeah. I just see that. Yeah. All right. So then, but when we consider the Fourier integral from negative infinity to positive infinity, all right, the general case, and we pay some special attention on two types of special cases. That's the even case and odd case. Even case and odd case. These two cases. Yeah. The reason also very simple, because when we represent our Fourier integrals on even and odd functions. Remember the symmetry, all right? So 1/2 of the integrals, sine, cosine, 1/2 of the integrals will give us 0. Then we can simplify our representation. Yeah. So that's the one of the most important reasons why we consider even odd functions. Yeah. All right, so here, we are here, all right? So here, let me use this time f of x, because here, look at the integral range, the limit from 0 to infinity. That's half of the x-axis, not the full x-axis. Okay? Only half of the x-axis. Yeah. All right. Half of the x-axis. Yeah. Here, look at this. The full x-axis, full x-axis. Yeah. Here, half of the x-axis. Yeah. All right. Yeah. Yeah. So now, but this is the f of x we used here. It's a general f of x. We do not require any symmetry, even odd function. So we do not assume that. So for any general f, we have, this is the definition of Fourier integral. How to calculate capital A function, capital B function. So these are the two formulas for these two functions. Yeah, but it's for the general case. Yeah. So I copy these formulas, put it here. Now we consider the special cases. This f function, first case, even function, second case, odd function, and we want to simplify the representation of this general formula. Okay? Yeah, typically, so even function, one term is gone. Okay? For odd function, another term is gone. That's simple. Okay? So that's the simplification. Yeah. But let's look at the detail a little bit. Yeah. All right. Yeah. So I use, these two regions to explain. Case 1, even function. F of negative x equals f of x. Symmetry. Okay? Here you see symmetry about y-axis. Yeah. All right. Case 2, odd function. F of negative x equals negative f of x. Yeah. So here I do not draw the graphs. Yeah. So last time I displayed. Here to save some space, so I do not display the graphs of these two functions. Now let's look at the Fourier cosine interval. Okay? All right. So here, look at A coefficient representation, B coefficient representation. Yeah. All right. B, when f is an even function, sine is odd function, right? Even times odd is odd function, right? Even times odd. So the new function is an odd function, but you take integral on odd function symmetric about y-axis, yeah, negative infinity, positive infinity, symmetric about y-axis, it's 0. Why? Because by the symmetry, we know integral, when we look at the meaning of integral from the geometric meaning, that's the area, right? Area under the curve, that's the integral meaning, all right? But this area, we consider sine the area. The area could be positive area, could be negative area. If below the x-axis, it's a negative area. By the symmetry, positive area, negative area cancel out. So the sum is 0. Yeah. That's the property for the, this whole function, odd function, although this f function is even times odd function, so we have that property, b equals 0. Then this term is gone, okay? That b part is 0, so our Fourier sine integral can be simplified in this way, okay? Only a of w function there, okay? So when you do calculation, you save your 1/2 of your work, okay? Yeah, so that's the first benefit, 1/2 of your work, okay? Yeah, so that's the reason the symmetry is good, okay? In math, usually symmetry is a good property, yeah. So that can save us a lot of work, yeah. Similarly, yeah, so here, let me continue, because you need to calculate a function in this formula, okay? But when you calculate, because f is a even function, even times even function, also even function, So the whole function even, then by the symmetry, the area is double the first half of the area, right? Double of the 1/2 of the area. So another, small simplification. Okay, yeah. So that's the cosine, Fourier cosine integral. Okay. Similarly, Fourier sine integral. Yeah. This time, our f function is odd. Then, when you look at the a function calculation, odd function times even function, odd function, its integral is 0. So you only have the b term. Okay, a term gone, or you only have the b term, and this b can be further simplified, double its first half integral. Yeah? Because odd function times odd function, even function. So even function, area double. Yeah. That's simple. Okay? All right. So we have the definition, these two, Fourier cosine integral, Fourier sine integral. Yeah. Yeah. So here, what are we doing here? Yeah, you may ask me, what are we doing here? So we are doing step by step toward Fourier transform. Yeah. Yeah. Because here, it's hard to jump from Fourier series to Fourier transform. In the middle, we need to do a lot of preparation. Here, we are doing preparation. Okay? So we're halfway there. Yeah. After we introduce these two Fourier integrals. Yeah. Then, another intermediate step before the Fourier transform, Fourier cosine transform, Fourier sine transform, another intermediate step. Okay? Yeah. So here, if we put these two formulas together in one formula, yeah, because we can plug in, right? You can plug in, all right? So then we can, actually we do not do anything new. We just manipulate our current formulas. We do not do anything new, but we just change a view. Yeah. Sometimes we change our view, understanding. We use a different angle to understand. We can define another important concept called Fourier cosine transform. Yeah. So let me show you. Yeah. Next slide. Let's look at the Fourier cosine sine transforms. Yeah. All right. Yeah. Laplace. Oh, let's do a simple example before we go to next topic. Yeah. Here, Laplace integral. Let's calculate. Okay. After we define the formula, let's do some simple calculation. Yeah. All right. Laplace integral. Yeah. This special expression. Yeah. The example, calculate the Fourier cosine, Fourier sine integrals of this special f function, e. E to the negative kx. Yeah. This one, let's just, where x greater than 0, k greater than 0. All right. To do that, let's just, here, I copy the formulas. Yeah. So I put the corner, okay? Top left corner, that's the Fourier cosine integrals. Yeah. All right. Then I put the Fourier, two formulas for the Fourier sine integrals, copy here. So we can, do the calculation. Yeah. 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 All right, so to calculate a function, capital A function, plug in the function, plug in, all right? Yeah. But, all right, we want to calculate this one, all right. Integration by parts, right? Yeah, because, So we can do that. Even we have infinity. So here, we have it from 0 to infinity. But we can use the limit way to calculate integration by parts. Limit way, okay? We take a limit. Yeah. All right. So here, the integration by parts, all right? Yeah. So that's the, after some computation, we get this. Before we, plug in these two limit bounds. Yeah. Before we plug in, okay? It's that one, all right? So then after we plug in the limit bounds, we get this expression. A of W, this expression. Yeah. Okay? Yeah. So then we can write the Fourier cosine integral expression. Yeah, by the formula. That's the formula. All right? Here we apply. F of x equals e to the negative kx equals this integral. Okay? Yeah? Integral. That's the first example. Yeah. Now you can see e to the negative kx equals this integral. Yeah. Yeah. If I ask you to calculate this integral, it may not be easy to get this function. Right? Think about it. Yeah. Yeah. I think about for myself, if I can calculate that, so I feel hard. Okay. Yeah. Yeah. I really need to find some, special technique. Yeah. Yeah. But here, because our Fourier integral, that's our result. Yeah. But that result, we have that. Here you can see how powerful is that result. Yeah. That formula is powerful. Okay? Yeah. So we get this expression. Similarly, for the cosine, so this is the, cosine version. Yeah. Cosine Fourier integral representation. Right. Then let's move to this side. Sine integral, Fourier integral representation, integration by parts. Yeah. So here, this is the, indefinite interval. Right. Indefinite, yeah, so here, this indefinite integral, yeah. Before we, evaluate at the two limit bounds, yeah. All right. So there, yeah. So after we plug in the two limit bounds, taking the limit, yeah. So we get this expression. Yeah. Then we can write f function in its Fourier sine integral, and we can write in this way. Yeah. See? All right. So you can see these two special integrals. Yeah. We know it's non-trivial, right? Yeah. So it's non-trivial. Yeah. So if you ask people to calculate, it takes a lot of time. It's non-trivial. Yeah. So that means the results, at least interesting. Yeah. So these two integrals we call Laplace integrals. Okay, just a name. Some history. Yeah, there is some history related to these two integrals. Yeah, here just as our practice. Okay, all right. Yeah, yeah, all right. Yeah. Then after this example, so. Oh, yeah. Oh, so we finish. Yeah, black screen. Yeah. So we finish part B. Yeah. So that's the part B. Now we can switch to part C. Yeah. Part C. Yeah. Part C, beginning, yeah. So Fourier transform. All right. All right. Yeah. So now the most important topic of this module and also of this class, Fourier transform, part C. Yeah. C.1. Let's do another round preparation. Yeah. Fourier cosine and sine transforms. Yeah. Yeah. So S. Okay. Yeah. So two transforms. Yeah. All right. Fourier cosine sine transforms. Yeah. All right. Well, yeah. So that's the. Yeah. I missed this formula. Yeah. The definition. Yeah. annoying. Yeah. All right, keep this cosine, right. So now I need to do animation a little bit. Yeah. All right. Up here, yeah, after, 4, 5. Okay, all right, yeah. Yeah, okay. Yeah, let's start, yeah. Yeah, I didn't see it. Yeah, all right, so here. All right. Importance of integral transforms. Yeah, first, let's talk about the general integral transforms. Laplace transform, that's an integral transform. Okay? If we recall the definition of Laplace transform, we use integral to define Laplace transform. Yeah. Here, we define a few more integral transforms, sine, cosine, yeah, but our goal, Fourier transform. That's the integral transform. Why it's important, right? Yeah. Why it's important? Yeah. Yeah. An integral transform is a transformation in the form of an integral that produces from given functions to new functions depending on a different variable. Yeah. I talked about this idea a few lectures ago. Yeah. Remember I talked about domain. Yeah. So when we do transform, we change our functions from time domain to frequency domain. Okay? Yeah. Yeah. Or time domain to S domain. Laplace transform from T domain to S domain. Okay? Yeah. Here we do the same thing. Yeah. So that's the meaning depending on different variable. Yeah. Yeah. Before the transform, we use T variable in our functions, for our given functions. But after the transform, we use S variable for that function. But that's for the Laplace transform. Yeah. Fourier transform, we use other different variables. Yeah. That variable is not important. Yeah. Just a different variable. Yeah. All right. Change the properties. What's the benefit of this method, transformation method, right? What's the benefit? Why you do that, right? Redundant, yeah, but it's not. Definitely it's not. The reason, the biggest reason we can use this sentence, because we can change the properties of the functions. Original function, we can change the properties. Yeah. After we convert those functions to different domains, we can get different properties, completely different properties, yeah, by changing the domain of the functions. Yeah. Yeah. So that's the power. So that's the, how things work. Yeah. This way. Transformation method. Yeah. Transformation method. Yeah. All right. Fourier cosine transform. Now we define Fourier cosine transform. So let's bring our Fourier integrals, the two formulas, calculate A function, then F function representation in Fourier cosine integral. So let's so here, let's recall the Fourier cosine integral even function from these two formulas. Even function, so we can do that. Okay, all right. So then, here, can you imagine? Yeah, can you imagine? Yeah, because here, first for the coefficient, we split. Yeah, here the two integrals. We want to. Yeah, so here, so compare these two integrals. Okay, compare these two integrals. The difference is only at the constant part. Okay. The variable, we make some change, okay? The v, we change to x. Yeah, but that's dummy variable. So that's not a, important change. Dummy variable, all right? Then the difference, we use root of 2 over pi here, not root. The reason is very simple. We treat this constant number as a square, and we take its square root to the other side, we split, okay? We put one square here, another square there, square root, yeah. Why we split? Yeah. Because we also want to do inverse transform. So root of the constant, that's for the, normal transform, and another root of constant, we put in the inverse transform. Yeah. So then even, right? So yeah, to be fair, right? You can treat it as a fair way. Yeah? But that's not a very important thing, because some people they do not split in that way. Okay? Some people they put this constant here, but when you do inverse transform, you do not have anything, just the one constant. Yeah. So many definitions also like that. Okay? But this way, also also very popular. Okay? Also very popular. Just split. One constant split. Root here, another root there. Yeah. Even split in this way. All right. Here you can see this, when we calculate a function, we treat it as a integral transform. Is it integral transform? Yeah. So here, compare the definition of integral transform. This definition of integral transform. Okay? Given original function f, we multiply this. We use a name before, we call it kernel, right? Yeah. Although we rarely use this name, this terminology, yeah, we call that kernel. Yeah. Because it's a special function. This function always fixed. Yeah. For cosine function, yeah, it's always fixed. If you change the kernel, then we get a different transform. Okay? Yeah. So the kernel concept. Yeah. Yeah. But here just let you know, original function, we multiply that kernel function, then we take integral, so we define a special transform. So here we call it Fourier cosine transform, and commonly for Fourier transform, we use this hat function. Yeah. That, hat. Yeah, I don't know. So how do you call it? Well, veg or hat? Yeah. Yeah. I just call it temporarily. All right. Yeah. So if I see some other way, so I can follow. Yeah. Because, all right. Yeah. That's the typical representation for Fourier transform. Yeah. All right. Yeah. All right. Then for inverse Fourier cosine transform. Inverse. Yeah. Because remember this, when we have Laplace transform, we also have inverse Laplace transform. Right? Otherwise, think about, if you only have Laplace transform, you don't have Laplace inverse transform, you solve your ODE in a different domain, you cannot get back, right? You cannot go back to the original time domain. Okay? Yeah, you cannot get the original solution. Yeah. So every time when we define a transform, we should also define its corresponding inverse transform. Otherwise, useless. Okay? Yeah. Because you convert it to a different domain, then you work, but you need to, after you get a result, you need to go back to the original domain by the inverse transform. Yeah. So here we do the inverse transform. Inverse transform means after we know this function, yeah, this transform the function, we take another integral, inverse transform, we get back to the original function. Yeah. Original function. Yeah. So that's just this formula, right? Yeah. Inverse transform here, then this function, we get original function. Okay, yeah. So that's original function. Yeah, here we put this root of constant. Yeah, put a transform function here. Yeah, here you see the same kernel function. Yeah, the nice thing is we use the same kernel function. Okay, so we recover the original function. Yeah. So that's the typical transformation method. Transformation method. Yeah. So our Laplace transform is a good example. Yeah. Good example. Yeah. Here we follow the same approach. Yeah. Yeah. All right. So next one for sine. Yeah. Because we have a sine transform, Fourier sine transform, and inverse Fourier sine transform. Yeah. Similar way. Yeah. We just this time for odd function. Yeah. So we just rewrite these two formulas. Yeah. So we do not create new formulas. We just rewrite these two old formulas. Yeah. So we define Fourier sine transform. Yeah. Just modify this formula a little bit. Yeah. Root of that constant, f, this het notation, sub s. Yeah. And this time the kernel is sine wx, kernel function. Okay. Yeah. All right. Then inverse Fourier sine transform. Yeah. Inverse. Yeah. Just rewrite this one. So you recover original function f of x, root of the constant. Yeah. So then the transform function. Yeah. The same kernel integral, you recover to the original function. Yeah. Yeah. Here you can see, these formulas, you can see some typical pattern. Yeah. You can see some typical pattern. Yeah. But yeah, if you compare with the Laplace transform, yes, now, yeah, because we're familiar with Laplace transform. Yeah. Here, if we want to compare Laplace transform, the inverse Laplace transform, we don't have that formula, right? Think about it. Inverse, it's hidden. Yeah, the inverse Laplace transform, we do not have explicit. Yeah, we like to say we do not have explicit formula. It's implicit. Okay? It's invisible. It's invisible. We only use the results. Okay? Yeah, we know. After we take Laplace transform, we have that function. Then we interpret inverse Laplace transform of that function. We get back. But no formula for that. Yeah? What's the formula of the inverse Laplace transform? We cannot see. But the good thing here is we can see explicit inverse formula. Inverse cosine, inverse sine. Okay? And for Fourier transform, we also have the explicit inverse formula. Yeah. From that point of view, it's better than Laplace transform, right? Yeah. More, because when we have a formula, we can do some manipulation on it, right? If it's invisible, it's hard to do manipulation. Yeah. Yeah. All right. Next, let's see. Other notation. Yeah, because after we define these transformations, we may like to use shorter notations to represent these famous transforms. Yeah. So these two, Fourier cosine, this kind of curved f sub c cosine. Yeah. If without c, that means a Fourier transform. Okay. Yeah. We will go there. We will get there. All right. But here, this version, cosine version. Yeah. So that's the notation. Okay. Because in our computation, usually we like shorter notations. Yeah. So we don't want every time we write this, long integral expression, right? Not efficient. Yeah. Not necessary. Every time we copy the full integral formulation, not very, very efficient. Okay? So we want some simple way. Yeah. All right. Notations. Yeah. The inverse transforms, inverse. Okay? Our usual inverse. Yeah, you know. Yeah. Yeah. These two versions, inverse. Yeah. All right. Yeah. Now the preparation should be, you know, very close to the point. Yeah. All right. But let's look at another C.2, linearity and the transforms of derivatives, properties. Yeah. Linearity. Yeah. Linearity, very simple. Okay. Yeah. These two transforms are defined by integrals. We know integrals have the linearity principle, you know, property. Linearity property. Yeah. So that is when you apply Fourier cosine transform on linear combination of two functions, you can, you know, use linear combination of their two Fourier cosine transforms. Yeah, that's simple. In your calculation, yeah, use this property. Yeah, very convenient. Yeah. All right. Similarly, for Fourier sine transform, you have this linearity property. Okay. All right. Next, the derivative property. Yeah. Yeah. Here, we are doing the same thing as we did in Laplace transform. Yeah. Laplace transform, we also have the, you know, derivative formulas. Yeah. Here, let's look at the first derivative formula. Yeah. When we have this derivative function, we take Fourier cosine transform on it, the first formula and the second formula. Okay? Yeah. Yeah. All right. Here, to see that, actually, it's pretty easy to see that. Yeah. Here we use the definition. This is Fourier cosine transform definition. Okay? Integration by parts. Right? Yeah. All right. Integration by parts. Yeah. But when you do integration by parts, at infinity, you need to take limit, right? Yeah. So then in the theorem, you need to have this, the limit when x approaches infinity, this f function approaches 0. So you need to have that condition. Yeah. You need to have that condition. So this term is gone. Okay? This term is gone, and yeah, well, not completely gone. The first part is gone. The 0 left. Okay? The 0, f0, it's a minus root this constant, f of 0, and here Fourier sine transform. Okay? W times Fourier sine transform, the definition. Okay? So that's the first formula. Second formula, similarly, yeah, so integration by parts, yeah, but this time you also use that limit, okay? Also use that limit, all right, yeah. But sine function at 0, it's 0, so the whole term is gone, okay, yeah, and you have this negative W times Fourier cosine transform function. Okay. Yeah, it's pretty easy to see it. Yeah. All right. All right, so this first derivative, then second derivative. Second derivative, we apply first derivative formulas twice. So we get second derivative, okay? Yeah, so next slide. Second derivatives of Fourier cosine and sine transforms. Yeah. All right. Yeah, so the final formula is like this. Final formula, these two, yeah. But here, let me calculate a little bit. Not very hard, but we need to use the first derivative formula. Apply twice. Okay, all right. The first one, apply the first time. Yeah, use the first formula, the first one. Yeah, but in this W Fourier sine transform of f prime, we apply the second first derivative formula another time. Yeah. Okay, yeah. Then after simplification, we get that, right? Yeah. Then you can see directly. Okay, we get that. The second one, we apply the first derivative of this fs formula the first time. Yeah. Fc formula the second time. Okay, yeah. Another multiplication. Then you can see, yeah, so you get that formula. Okay? Yeah. So here you can see from the form, pretty close to what we saw in Laplace transform. Yeah? Laplace transform will have similar structure, at least. Yeah, slightly different. Okay? Slightly different. Yeah. But here it's a pair of transforms, right? Cosine, sine. Yeah. Because the cosine formula, you need to use the sine transform expression. The sine formula version, you need to use the cosine transform expression. Yeah. So coexist, a pair of function, yeah, a pair of transforms coexist. Yeah. So that property. Yeah. All right. Yeah. So that's the, some properties. Yeah. All right. Example, calculate Fourier cosine transform. All right. So let's calculate Fourier cosine transform for this function, f function, e to the negative ax, this function. Here we use the property. Here we use the properties. Okay? Yeah. All right. Solution. The property, we know the second derivative. Yeah. Here we want to use the second derivative. Yeah. Not the first derivative, second derivative. Okay? Here we use the second derivative formula, not the first derivative formula. Do you know why? Yeah. Yeah. We do not use the first derivative formula. We use the second derivative formula. Yeah. The reason is simple. Remember, a pair of transforms, sine, cosine. The first derivative, you need to use sine. Yeah. The cosine of the first derivative, you need to use the sine version, right? Twice, second derivative, you get back to the cosine, right? Cosine, you get back to the cosine again, so that's more convenient. Otherwise, it's not a cosine, it's a sine. You need to calculate the sine, but you do not need to calculate the sine transform, right? Yeah. So here, that's the reason we need to do double prime operation. Yeah. Then, let's apply this double prime Fourier cosine transform formula here. Okay. Yeah. So you see, yeah, by the linearity principle, yeah. All right. Yeah. Yeah. So that, because here, when you apply Fourier transform of this function, linearity principle, you take a squared out. Yeah. 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 So here, right. So this formula, before we apply the Fourier cosine transform, we have this one. Then we apply that formula. Okay? Yeah. That formula, yeah. So the first time we apply linearity principle, we take a squared out. Yeah. This expression, we can use that formula. This expression, we apply that formula. Okay? All right. Negative w squared fc transform of f. Yeah, same transform. See? Yeah. This equation about the same function. Then we can solve for this function. Yeah. So the function expression is like that. Okay? Yeah. So the Fourier cosine transform of f function is this one. All right. Yeah, that's a simple example. Yeah, just calculation. Show you how to use this formula to calculate. Yeah. All right. Yeah, so now we are ready. Yeah, because after all the preparation, now we are ready to learn Fourier transform. Okay? C.3. Yeah. Complex form of Fourier integral. Well, still not there yet. Another topic preparation. C.3. But here you can see we get another step closer. Because Fourier transform, we use complex. Okay? Yeah, here, the complex. Yeah. Some students are not familiar with the complex numbers. Okay? They try to avoid. Yeah. So sometimes we try to avoid complex numbers. Yeah. But sooner or later you cannot avoid. Okay, yeah, especially for your engineering students. Yeah. So sooner or later you have to, because complex numbers is a powerful tool, powerful problem-solving tools. Yeah, if you avoid, you miss a powerful tool. Yeah. So you want to pick that up. Yeah, powerful tool. Yeah. Here, the complex form of Fourier integral. Yeah. At this point, Fourier cosine, Fourier sine, they both real forms. They're both real form. No complex, no I. All right. But now we want to combine Fourier cosine transform, Fourier sine transform together. But after we combine, we use the Euler formula, we get a complex expression. E function, e to the I times some expression. Yeah. So that will be used as the Fourier transform definition. Yeah. All right. Yeah. Let me just do a little preparation. Then we take a break. So after the break, we can look at the formal definition of Fourier transform. Yeah. All right. From Fourier cosine and the sine forms to complex form. Yeah. Start from Fourier integral. Yeah. Yep. So this version, the Fourier integral, I'm writing here this version. Remember, this f function, we do not require even function. We do not require odd function. It's the general function. Yeah. So here we get back to the general function. Because when we define Fourier integrals, we need to work on the general function. Not even function, not odd function. Fourier transform is defined on general function. So here we need to go back. So although sine, cosine forms, sine form is for the even function, cosine form for the even function, sine form for the odd function, two special cases. But when we combine, we need to extend to the general function. Yeah. Yeah. So here the derivation. So here the derivation, actually, we get some inspiration from sine cosine transform. Inspiration. Yeah. So what I mean, inspiration here, it's not a rigorous proof. It's not a rigorous proof. Okay? Inspiration is we use the existing formulation to give us some reasonable new formulation ideas. That's the meaning. Okay? New formulation ideas. But it's not a rigorous logical reasoning. All right? Rigorous proof. Yeah, rigorous proof. Yeah. Because sometimes we need to use imagination. We need to jump some steps. And those steps, you may not have the rigorous deductions. Yeah. Yeah. So here, mainly inspiration. Okay? All right. Yeah. So now the formulas we are familiar with here. Yeah. All right. First, we plug in. Okay? Yeah. So we plug in. All right. Yeah. A expression, B expression, so we write it in one big formula. Yeah. Yeah. So here, I'm talking about how researchers discover some new results from old results. Yeah. So here, another situation. Researchers discover some new results from older results. Yeah. So they need to first thing they need to manipulate on the older results first. Okay? Yeah. So they try to see how far we can go, yeah, how far? Okay, so they try, different, it's like doing experiments. Yeah. All right, so now they do this manipulation, plug in, okay? Yeah. But the expression inside the brackets, inside those brackets, we know it's a formula, right? Yeah. Yeah. Sum, cosine, sum of angles, right? Some cosine formula for sum of angles, that formula. Yeah. Or here, probably the difference of angles, right? Yeah. Minus the difference of angle. Yeah. So here, this formula can be simplified to f function times cosine of wx minus wv. Yeah? Yeah. So the new form, okay, the first step. All right. Then, yeah. All right, so here, yeah, because here, inner integral is on the full x-axis, but the outer integral is on half-axis, right? Inner integral is on full x-axis, but outer integral is on half-x-axis. Why? Because we start from the cosine transform, that's for the even function. Even function will only work on half-axis. But now we want to go back to the original function, so we want to switch to the full axis. Okay? Yeah. So here it's the inspiration. So here it's not a deduction. Okay? Yeah. Because if you say the deduction, then you have some, logic hole there. Logic hole there, right? So here the inspiration. When we see the formula here, we get this inspiration. All right? So we should extend to the full axis, but at the same time, we need to divide it by 2. Okay? 1 over 2 pi. Yeah? Yeah, because we doubled it, right? We doubled it. Yeah. But this is not necessarily an even function anymore. Okay? That could be extended to non-even function, the general function. Yeah. So that's why I say inspiration, okay? Not a rigorous deduction. Yeah. All right, let's take a break. Yeah.